you can see the screen which I have shared with you. So if we can quickly recap which we discussed in the last class, we started with the fluid element kinematics, and in that we discussed that there are four types of deformation of a fluid element when it flows uh, through the any flow. So these four types of deformations are number one, translation. Then we have got a linear deformation, then rotation, and the last one is the angular deformation. So in translation and rotation, they are rigid body motion, and in this the shape and volume does not change. But in the linear deformation, the volume changes, and in angular deformation, shape changes. And for the translation, there is no velocity gradient. It means that within the element, so it means that the element has got the same velocity at each point, while for the linear deformation, as we discussed in the last class, that we need some normal velocity gradient. So if I let me open the whiteboard, and then we can. So this was just a recap. So let me. So normal velocity gradients, they are partial u by partial x, partial v by partial y, and partial w by partial z. While the tangential velocity gradients, there are three normal velocity gradient and six tangential velocity gradients, like partial u by partial y, partial u by partial v, partial v by partial x, partial v by partial y, and partial w by partial x, and partial w by partial y. So for the linear deformation, the necessary condition is that we need to have normal velocity gradient. And for the rotation and angular deformation, we need to have tangential velocity gradient. So if you remember that in the last class, we discussed about the volumetric dilation rate, change in volumetric dilation rate, which is the rate of change of volume per unit volume in the all three directions. So we noted that volumetric dilation rate is partial u by partial x plus partial v by partial y plus partial w by partial z. And then afterwards, we noted that for the incompressible flow, the volumetric dilation rate is zero because there is no change in density. So it means that if the density cannot change, so then the volume cannot also change because the total mass would remain the same. So mass is the product of volume into density. So if the density is not changing, so volume cannot change. So it means that for the liquid, we usually say that volumetric dilation rate is equal to zero. But for the gases, because they are compressible, so in that case, we have got non-zero volumetric dilation. Afterwards, we discussed about the rotation, that how we can find the rotation for a fluid element. For that, as I told you just now, that tangential velocity gradients needs to be there. So in this case, we have got uh, tangential velocity gradient like partial v by partial x, as I am showing with the mouse cursor, and then partial u by partial y. So if you can see that one angle is this delta alpha, that is counterclockwise, and delta beta is clockwise rotation. So if we calculate the value of the angular velocity, that after doing some mathematical manipulation, it comes out to be partial v by partial x, as we discussed this thing on whiteboard in the last class. And then similarly, the angular velocity for line OB, that comes out to be equal to partial u by partial y. So the rotation of the element about the z-axis is the average of the angular velocity. So if we take the now, because these two are in different directions. One is counterclockwise, which is delta alpha, and the delta beta is the clockwise direction. So we are taking counterclockwise as the positive direction, and then we add them. So because partial u by partial y is clockwise, so it has been added as negative. So omega z comes out to be 1 by 2 partial v by partial x minus partial u by partial y. So it is about the z-axis. Similarly, we can find the rotation component about y-axis and x-axis. So if we do that, if we follow the same procedure, we can find the value of wy and wx. So the last thing we discussed in the class, that was that omega vector is we can write it omega xi plus omega yj plus omega zk. And second thing we discussed, that omega is half of curl of velocity field. So curl of velocity field, as I mentioned in the last class, that is very easy to derive. That is equal to half into ijk partial by partial x, partial by partial y, partial by partial z, and uvw. So if we expand it, we can easily write 1 by 2 into partial w by partial y minus partial v by partial. And so it is a kind of determinant. So we can write it like this: I plus, it would be partial for the y, it would be partial u by partial z minus partial w by partial x j component plus half into partial v by partial x minus partial u by partial y. So this is k component. So it means that this component is wx, this component is wy, and this component is wz. So is there any question up till this point? Any query? Okay. So it seems that everything is clear. So that is very promising. So now if we write the formula for wz here, WZ is equal to partial v by partial x minus partial u by partial y. So it would be, if we want to have zero rotation, so in that case, Wz would be equal to 0, and we can write for zero rotation, we can write Wz is equal to 0, and in that case, partial v by partial x is equal to partial u by partial y. So if I show you on the slide, that would it mean that partial u by partial u by partial y is equal to partial v by partial x. So it means that if we have got partial v by partial x in counterclockwise, then the same counterclockwise distance would be there for the partial u by partial y. So on the whiteboard we can show it by on the best line. So it means that we mean to say that we can have something like this. So it means that this is also delta alpha is also counterclockwise, and delta beta is also counterclockwise. So it means that now the fluid element has been rotated without having any kind of deformation. So it has been rotated as a rigid body. So it means that okay, and one thing I forgot to mention, that vorticity, which is the characteristic of flow field, that is twice the 2 multiplied by the rotation vector. So it tells about the rotational characteristics of a fluid. So now we need to discuss about pure rotation and pure angular deformation. So as I have discussed that in case of rotation without angular deformation, partial u by partial x would be equal to minus partial v by partial x. So it means that if this is going this way, it should also go this way. So partial u by partial y should be equal to minus partial v by partial x, because here partial v by partial x is shown in the clockwise direction. So in order to have rigid body motion, it should have negative value, because it means that it should go in the clockwise, in the counterclockwise direction, as I shown on the whiteboard. Secondly, if we want to have angular deformation without rotation, so without rotation means that we have got this Wz is equal to 0. In that case, partial v by partial x would be equal to partial u by partial y. What does it mean? That the element has not been rotated
सर
about
आपकी
it.
सर आवाज ब्लैंक आ रही है सर
जी,
कभी सर मीडियम हो जाती है कभी ऊंची हो जाती है सर कभी स्लो हो जाती है कभी हाई हो जाती है
okay, okay. I would maybe I would see to that. So is it okay now at the moment? Can you please confirm?
No, sir.
यस सर
जी, अब ठीक है
सर बिल्कुल क्लियर नहीं आती सर
बेटा। अब ये कॉलेज का इंटरनेट का इशू है, आई एम नॉट श्योर। मैं भी
से आ रही है आवाज आपकी
अच्छा अच्छा, ये रिकॉर्डिंग हो रही है, ठीक है। तो इफ देयर एनी पोर्शन ऑफ माय lecture which is not clear, you can always listen to it afterwards, but hopefully things would get better as we proceed with the lecture. So
Sir,
just
I think the issue is not with the network. I think we are not getting you clearly, so there is no clarity in the voice, I guess.
okay, so what should I do? What do you recommend?
Uh, that is a question, sir, but I don't know
Dishan
about that.
Ali,
Yes, sir.
Dishan Ali, you are saying that my voice is not clear. Is it not audible or you cannot understand it?
Sir, sometimes it becomes low, sometimes it becomes high. It just fluctuates, and it's quite difficult to understand.
Okay, is it all right at the moment? Dishan Ali, can you hear me? Dishan.
Yes, sir. It's quite better now.
Okay, maybe I would hold this microphone in my hand, so it would be better. So if it gets low again, then please do let me know. So in the meanwhile, we continue with the lecture, right? So we were talking about. Let me repeat it. That rotation without angular deformation occurs when partial u by partial y is equal to minus partial v by partial x. It means that this OB line, OB the prime line, it should be on this side. So it means that delta alpha and delta beta should be in counterclockwise direction, because here delta alpha is in the counterclockwise direction and this delta beta is in the clockwise direction. So if we can make it in the counterclockwise direction, as I shown on the whiteboard, like this. So it means that there is no angular deformation, but only rotation about its axis, which is at this point, which I am showing with mouse cursor. Okay, second point, that is the angular deformation without rotation. It means that there is no net rotation of the element, but only change in shape. So that can only occur when we have got zero rotation. So zero rotation would occur if we go back. In this formula, when would zero rotation occur? When wz is equal to 0, which means partial v by partial x is equal to partial u by partial y. So in this figure, if delta alpha is equal to delta beta, so because delta alpha is counterclockwise, delta beta is clockwise, so it means that if we add them, the result would be equal to 0. So if that is the case, then we would have angular deformation without rotation. Zishan Ali, can you hear my voice now clearly? Just to
Yes,
confirm.
yes,
Okay.
sir. Yes, sir.
Okay, thank you. So now, if we want to have both phenomena in which there is rotation as well as angular deformation, then if partial u by partial y is not equal to partial v by partial x, then we would have simultaneously rotation as well as angular deformation. So in case when corresponding tangential velocity gradients for a rotation vector are unequal, it means that partial u by partial y is not equal to partial v by partial x. Both angular deformation and rotation occurs in zx. More generally, if curl of velocity field is equal to 0, then the rotation and the vorticity are 0, and the flow field for which this condition applies, they are termed as irrotational. So if you remember the assumption of Bernoulli equation, which you discussed in chapter number, I think, 3 in your FM1. So one condition for the applicability of that Bernoulli equation was that the flow should be irrotational. So now maybe you can understand it better, that what it means to be irrotational when we have curl of velocity field is equal to 0. And other assumption for the Bernoulli equation was steady flow and incompressible flow, and the flow should be along a streamline. So now the last concept here is rate of shearing strain. So we can determine the change in the original right angle So if we want to know that how much shape has been changed, then we can say that we can add delta alpha plus delta beta to get the change in the original right angle or original shape of the element, and that would be equal to delta alpha plus delta beta. So if delta alpha is equal to minus delta beta, which is the case which is shown here, then we would have if delta alpha is equal to minus delta beta, then it would be shedding strain is equal to 0. So that would be the case when there would be a gradient in this direction, which means that we are talking about pure rotation, right? So we can get the value of rate of shedding strain, that would be equal to partial v by partial x plus partial u by partial y, and that would be if we put this shedding strain is equal to 0, then the condition would be partial v by partial x is equal to minus partial v by partial x. So partial u by partial y is equal to minus partial v by partial x. It means that for this case we are talking about pure rotation. So shedding strain 0 means that there is no change in the shape of the body. So it is only rotating there, rotating about the axis, pure rotation, and that would be only the case when we have got this this partial v by partial x on the this side. So it means that it is kind of rigid body rotation. Now we can have any query if you have got anything which you couldn't understand in these 4 types of deformations, then you can ask me now. Otherwise, we can continue with some numerical problems for these 4 cases. Nishan Ali, everything clear?
Yes, sir.
Okay.
सर उसका
So, yes.
सर कुछ
Please
नहीं
ask. No, please ask. Don't be shy. If you have got any question, you are free to ask at any time.
सर वो यस
जी
सर वो
पूछिए।
राव ने पूछा था सर वो दिशान अली ने मैसेज किया था पहले मुझे कि ना मेरा वो माइक नहीं जा रहा था सही, तो मैं उसकी तरफ से रिप्लाई देने लगा था, उसका शायद अब ठीक हो गया होगा।
ठीक है जी, थैंक यू वेरी मच। आपका क्या नाम है बेटा?
सर उमेर।
Okay, so please whenever you want to ask anything, I would request that please state your name first so that I can interact with you. I can speak with you directly, so that would be better for the communication purpose. Thank you very much. Okay, so if you understand these 4 types of rotations or deformations, then we can. So these are the 4 deformations. Just to summarize: translation, linear deformation, rotation, and angular deformation. So just to make sure that we are on the same page, translation and rotation, they are rigid body motion. There is no change in volume or shape of the element. But for the linear deformation, there is change in volume, but there is no change in shape. But for the angular deformation, there is no change in volume, but there is change in shape. Okay, so now we go towards a few numerical problems, which we can see that to see that whether the flow is having some kind of deformation, linear deformation, rotation, or angular deformation. So let me go to the. Okay, so this is the first problem. Here we have got the 3 components of velocity in a flow field. So u is equal to x square plus y square plus z square. So let me write it. U is equal to x square plus y square plus z square, and then we have got v is equal to xy plus yv plus z square. xy plus y plus z squared, and then w is equal to, let me write it, z squared. Okay, and w is equal to minus 3xz minus z squared by 2 plus 4. Minus 3xz 3xz minus z squared by 2 plus 4. Okay, so this is the velocities in a given flow phase. So first of all, we need to determine the volumetric dilation rate for this flow phase. So volumetric dilation rate, if you remember, that was equal to del dot v
सर ये आपने सर यू वी और डब्ल्यू के साथ जो क्वेश्चंस लिखी हैं सही हम ड्राइव करेंगे का इनको बस याद करना है?
दोबारा बताइए। ये वाले जो
सर ये
आपने
जो यू
बेटा, ये अगर आप देखें ना गौर से, ये क्वेश्चन की स्टेटमेंट में गिवन है। उमेर, इज इट उमेर?
यस सर।
उमेर, ये देखें ना क्वेश्चन की स्टेटमेंट में ये जो यू वी और डब्ल्यू की ये जो है ये फार्मूला गिवन है ना, ये आपको गिवन होंगे।
यस सर, मैं था ऊपर स्टेटमेंट मैंने पढ़ी न्यूमेरिकल प्रॉब्लम्स, मुझे पता चल जाता है इसलिए वो मुझे। यस सॉरी सर।
That's fine. No, that's fine. There is no need to apologize, even if you ask some very simple question. This is your right. You can ask always. So don't be apologetic in any way. No, there is no need to be. Okay, so del dot v is equal to partial u by partial x plus partial v by partial y plus partial w by partial z. Now, if we if we can find the value of partial u by partial x from the top equation, that would be equal to 2x plus partial v by partial y, that would be equal to, if we take the derivative with respect to y, that would be equal to x plus z plus there is some distortion in voice. Do you want to add anything? That would be equal to partial w by partial v would be equal to minus 3x minus z, right? So I hope that you understand that how we have done this, how we have written partial u by partial x. We have kind of just taking the derivative and put the values here. So now, because if you kind of simplify it, that would be equal to 3x plus b minus 3x minus b. So this would be cancelled. So volumetric dilation rate is equal to 0, which means that this flow is incompressible. This flow field is incompressible because the volumetric dilation rate is equal to 0. Now the second thing which we want to determine here, that is the expression for the rotation vector. So we need to find the expression for the rotation vector. So for the rotation vector, we know that for the w, first of all, we write the expression for the wx. So let me do it somewhere here. Wx would be equal to 1 by 2 partial W by partial Y minus partial B by partial Z. Now, if we see partial W by partial Y, that would be equal to partial W by partial Y would be equal to 0. So that would be 0 minus partial B by partial Z. It would be equal to Y plus 2Z. Similarly, Wy, that would be equal to half into partial U by partial Z minus partial W by partial X. So that would be equal to half into, if we take partial U by partial Z, that would be equal to 2Z partial U by partial Z, and partial W by partial X, that would be equal to 0. I hope that you understand this. Okay. Partial W by partial X not 0, it should be, just a minute.
Minus 3.
Minus, it shouldn't be 0. It would be minus 3Z. I didn't see that X there, so it should be minus 3Z. Someone has rightly pointed out. Similarly, we can find WZ, that would be equal to half into partial V by partial X minus partial U by partial Y. So that is equal to half into partial V by partial X, that would be equal to Y, and partial U by partial Y would be equal to minus 2Y. Right, so we can write, now we can see that I have to go down, so we can write this.
Sir,
Yes.
I think WY में हमारा जो 2Z plus 3Z आएगा.
Okay, let's see. WY में क्योंकि माइनस पार्शियल W by partial X है, you are talking about WY.
Yes, sir.
WY में partial W by partial X. Yes, it should be plus. Thank you very much. Because, it is minus, so minus into minus would be plus. Thank you. Maybe you can mute your mic. For the time being, if you can mute your mic, it would be good. So, who was that who pointed out this? Please state your name so I can also get to know your names as well. Okay, thank you. Okay, we understand this is not the ideal way of learning, but we need to get through this. We would. Okay, so if we can write the rotation vector here, that would be equal to W would be equal to Wx I plus Wy j plus Wz k. Right. So Wx value was equal to minus y by 2 plus v I plus 5z by 2 j plus, sorry, it should be minus here, minus y by 2 k. So this is the rotation vector. So it means that the flow field is incompressible, but it is not irrotational, because the rotation vector is not equal to 0, so the flow field is irrotational. It is rotational, basically. The flow field, we can write that it is rotational flow field. Okay, so this was the first numerical. Now we can do the second numerical, that is an incompressible viscous fluid is placed between two large parallel plates. The bottom plate is fixed and the upper plate moves with a constant velocity u. So it means that the upper plate is moving with the constant velocity u. For those conditions, the velocity distribution between the plates is linear and can be expressed as u as a function of y, that is equal to u into y upon b. B is the distance between these two plates, and y is the vertical distance starting from the bottom plate. So if you put y is equal to 0 at the bottom plate, the velocity would be equal to 0, and when you put y is equal to b, which is the distance between the plate, the surface, the value of velocity at the top plate would be equal to capital U. So this kind of flow is called Coet flow, and we are going to discuss this flow at the end of this chapter in detail after the derivation of Navier flow equation. And this is the flow which usually happens in all the bearings which are installed in our turbo machinery. So in bearing one, the inner cylinder is, or the inner ring is attached with the shaft, and the outer ring is moving with the rotor. So that is the practical application of this flow, and we call it Coet flow, and we are going to discuss it at the end of this chapter also. So in this, now we need to calculate the volumetric dilation rate. So let's do it on the whiteboard. The velocity is given, velocity vector is given as it is equal to y upon b u, which is in x plus 0 j plus 0 k. It means that there is no vertical ball normal velocity or into the board velocity. So v and w velocity, they are equal to 0. Only u velocity is non-zero, which is given by y upon b into u. Anything you want to add, Hassan?
No, sir, clear.
Okay, so because someone unmuted the mic, so I just thought that someone wants to add something. So now we need to find the volumetric dilation rate here. So for this, first of all, volumetric dilation rate, that would be equal to, that would be, in this case, it would be partial u by partial x plus partial v by partial y plus partial w by partial z. So we know that v and w, they are already 0, so no need to calculate those gradients. If we calculate partial u by partial x, that is also equal to 0, because there is no x term in the u velocity, which is y upon b into capital U. So it means volumetric dilation rate is equal to 0. And then we have, this was the first part, which was quite easy. And then the second part is the rotation vector. So in this, the rotation vector would be only in the about z direction. So it means, because x and y would be equal to 0, so we can find the rotation vector. So if we find the rotation about v, so wz would be equal to, because it is kind of two-dimensional flow, so it would be half into partial v by partial x minus partial u by partial y. So partial v by partial x is equal to 0 here, and partial u by partial y would be equal to u upon v. So we can write minus u upon 2b wz. So rotation vector would be equal to 0I plus 0j. There is no rotation in x and y, and in for the v direction it would be minus u upon 2b k. Right? So I have just written 0I plus 0j just to emphasize that wx and wy components, they are equal to 0, because it is two-dimensional flow, so the rotation can only occur in the about the z axis. So this was the second thing, and then we need to find the vorticity. So we know that vorticity is the double of, so vorticity, that is shown by this symbol, that is equal to 2 into omega. So it would be equal to minus u upon b k, and then vorticity. After that, we need to find the shading rate of angular deformation, which is the shading strain in this case. So that would be equal to omega, and it would be equal to partial v by partial x plus partial u by partial y. So if you are wondering that from where we have written this equation, so if we go back here, this one, rate of shading strain or rate of deformation, we also call it rate of deformation, that is partial v by partial x plus partial u by partial y. So it is only in the about the z axis at the moment. So we can also find the rate of shading strain about x axis and y axis, similarly as we did for the rotation vector. So if we try to find that, so partial v by partial x, that would be equal to 0, and partial u by partial y, that would be equal to u upon v. So we have found the rate of deformation, angular deformation. Here it is vorticity. This is vorticity. This is rate of angular deformation. This is rotation vector, and then the last one is the first one was dilation, volumetric dilation rate. Volumetric dilation rate. So this was all about this topic. Now we are going to start deriving the Navier-Stokes equation, which is the set of continuity, momentum, and energy equations. So first of all, we would apply the conservation of mass principle to the system. So okay, before we do that, there are some homework problems from Munson book, which are 6.2, 6.3, 6.6, 6.8, and 6.10. Please have a look at these problems at your own time, and try to solve them if you have got the manual, and then we can discuss if you have got any query with those problems. So these are the minimum number of problems which you need to do it at your own time and understand these problems, so that it can give you the complete knowledge of this topic. Now we are going to discuss the derivation of Navier-Stokes equations, which are usually the governing equations for the viscous incompressible unsteady flow field. So that is the most realistic thing we can have for the subsonic flows. So we start with the conservation of mass. So in the Cartesian coordinates, we are going to derive it. So we can send it to the cylindrical polar coordinates as well for some other flow fields, but we would start it with the Cartesian coordinates. So if you know that conservation of mass principle, that is the mass of the system remains constant. So it means that mass cannot be created nor it can be destroyed. So we know it from thermodynamics as well. So a system moves through the flow field. So we write dm of system by dt is equal to 0. So if you remember that you have learned the concept of extensive property and intensive property. Is that right? What is extensive property?
So the extensive property
That
depends
depends on
on mass.
On mass. So it means that if I write mass, that is the one example of mass that is represented with the symbol m. So that is the example of extensive property. So what would be the intensive property in this case for mass? If capital B is mass, so small b, which is intensive property, that would be divided by mass, that would be equal to 1, right? So for the mass, the intensive property would be 1, because intensive property that is independent of mass, so it means that we need to divide it by mass, so it becomes equal to 1. So because we have just mentioned that from the conservation of mass principle, dm system by dt is equal to 0, right? So now, because we cannot apply this on a system, because we have to follow all the particles, so it is better that we kind of fix a volume in space, and then we study that how the mass goes through that controlled volume. So it means that we need to make use of that Reynolds transport theorem. So that transport theorem, if you remember, that is equal to dB by dt is equal to partial rho by partial t controlled volume into rho b dV plus control surface and rho b v dot n dA, right? So as I mentioned here that capital B in this case is that is equal to mass of the system. So I'm going to replace that here. That is equal to mass, and this B for this case it would be 1. Here it should always be 1. Okay, so now we are going to take a differential control volume and apply it there. So if I draw a differential control volume here, sorry. So this is our cubic type of control volume. So in this we know that this is x direction, this is y direction, and this is out of the board, that is z direction, right? So if we have got the property is known at the center, that is at the center of the cube, if those that property is rho into u, because here rho into u be the property which is going out and into the system. If this distance is delta x, this distance, that is delta y, and this distance, that is del z. Okay, so if the property value at the center would be del u, what would be the property here at the left face and the right face? Anyone? What would be the value at the right face or the left face? Because we did it in the previous lecture by the use of Taylor series. Okay? So if I kind of write it here, that would be, it would be rho u plus partial by partial x rho u into del x by 2. And if we want to calculate the, because we know that mass flow rate is rho v into area. Area is the perpendicular area through which it flows. So for this, it would be del v into del y. And why there is del x by 2? Because the distance between this point and the right face, that is equal to del x by 2. So I think the time is over for this class. Is that right?
Sir.
What is the time for this class to be over? I think it is 10:25. So let me. I think we keep our discussion up to this point, and we would start from here in the next class. Right. So thank you for your. Let me download the attendance. So I have downloaded the attendance, and I would see you in next class, which is going to occur next week. So I would share the lecture slide with the
recording stop कर दे
जी मैं कर देता हूँ. So I would